In 2026, the physical delivery of electricity has surpassed silicon lead times as the primary risk to global AI infrastructure. This chart tracks global AI compute demand against available grid capacity. Between 2026 and 2030, nearly 100 gigawatts of new data center capacity is projected to come online globally. That 100 gigawatt surge roughly doubles the total existing data center capacity in many major tech markets. Despite this demand, nearly 11 gigawatts of announced projects are currently stalled in planning, with no construction underway as of March 2026. Power procurement lead times have officially eclipsed hardware lead times. Securing the wattage to run a GPU now takes longer than manufacturing the chip itself. Energy procurement is now the single most critical supply chain asset for corporate survival. Early hyperscale data centers were built to handle web traffic and cloud storage, drawing steady, predictable loads in relatively modest facilities. Modern AI workloads require massive, tightly packed compute clusters. This high-density hardware demands a different class of physical infrastructure for cooling and power delivery. Training a single frontier model consumes the electricity equivalent of thousands of households, drawing maximum capacity continuously for months. Inference at scale multiplies this demand globally, as everyday AI queries pull power across thousands of active GPUs simultaneously. By 2030, these localized AI data centers are projected to rival the total power consumption of entire nations. The legacy utility grid was engineered over a century for distributed, low-density loads. It is now physically buckling under the strain of these concentrated vacuums of compute density. The first physical failure point appears in the interconnection queues. In the US, Europe, and Asia, the pathways to connect new data centers to regional substations are completely gridlocked. Utility companies are currently quoting 3 to 5 years just to approve a new facility's grid connection. Hyperscale facilities require massive industrial equipment to step down transmission voltages for server use. They cannot simply plug into the line. High-voltage transformers have become the primary single point of failure in this physical supply chain. Severe limitations in manufacturing capacity and raw material shortages have pushed transformer delivery lead times to between 2 and 3 years. Local friction compounds these hardware delays. Environmental permitting, community opposition to land use, and concerns over rising electricity costs further slow the rollout. Consequently, half of all announced data center projects slated for 2026 are facing immediate delays. Multi-billion-dollar software initiatives are currently paralyzed by an inability to source 20th-century analog electrical hardware. Major operators including AWS, Google, Meta, and Microsoft are abandoning standard utility timelines. They cannot afford a 5-year wait for grid upgrades. Their immediate response is to prioritize hardware upgrades at existing, already powered sites, rather than breaking ground on new footprints. Retrofitting these sites with specialized cooling and power systems is inflating construction costs by 7% annually. To bypass the grid bottleneck, operators are shifting to behind-the-meter generation, producing their own power directly inside the data center footprint. This strategy involves deploying natural gas peaker plants, utility-scale battery arrays, and planning for small modular nuclear reactors on site. They are also signing long-term power purchase agreements for dedicated renewable sites, securing baseload power while attempting to hit decarbonization targets. Battery storage has transitioned from an emergency backup to standard daily infrastructure used to manage peak computational loads. To compete in the AI race, software and cloud companies are operating as independent power producers. Upstream, the physical manufacturing of AI silicon is governed by the same constraints paralyzing the data centers. Manufacturers of essential grid switchgear are fighting for the same constrained raw materials as the rest of the heavy industrial supply chain. For semiconductor fabs running 24/7 lithography and etching processes, grid reliability is a life or death metric. Even micro-interruptions in power result in ruined wafers and catastrophic financial losses during the advanced packaging and lithography stages. Global geopolitical tensions frequently disrupt the shipping routes for the fuels required to generate this power. Reliance on natural gas and LNG exposes fab operations and backup data center generators to massive price swings. Predictable, uninterrupted baseload energy is the fragile physical thread holding the entire AI hardware supply chain together, from initial etching to final deployment. Governments now view high-density compute clusters and their energy pipelines as sovereign national security assets. Many nations are forcing localization, building region-specific computing grids to protect their economic competitiveness. Analysts call this trend AI balkanization. Gartner predicts that by 2027, 35% of countries will be locked into isolated, region-specific AI technology stacks. Scaling globally now requires hyperscalers to navigate a maze of varying data sovereignty rules and distinct regional energy policies. China's 15th Five-Year Plan prioritizes this model, mandating accelerated computing infrastructure and massive energy system upgrades. Beijing is building integrated national computing networks with explicit energy crisis response capabilities to guarantee self-reliance. The rollout of AI has become a territorial, physical land grab for sovereign energy dominance. The AI boom has permanently linked advanced digital processing to the mechanics of physical energy systems. Global data center spending is projected to reach $330 billion annually, yet this capital depends entirely on overcoming physical grid bottlenecks. Holistic energy resilience planning has replaced just-in-time hardware procurement as the industry standard. Investors are now strictly factoring grid access and baseload strategy into their foundational due diligence for any new tech project. What do you see as the biggest barrier to AI infrastructure growth in 2026? Legacy power grids, hardware constraints, or regulatory policy? Let us know in the comments below.